Hi, I'm Brian Rabel, and I'm the leader of the experimental accelerator-based neutrino effort here at UW-Madison. We have a group of 6 people, 2 faculty, myself and Jenny Thomas, a visiting professor from University College London, 2 postdocs, Tom Carroll and Adam Lister, and 2 graduate students, Harry Hausner and Tian Xie. Now, what we do is we use beams of neutrinos created at Fermilab and directed towards a detector several hundred kilometers away in order to understand something called neutrino oscillations, which is the process of neutrinos of one flavor changing into neutrinos of another flavor. What's really happening is that the neutrino flavors that we have identified, the muon, the tau, and the electron neutrino, are actually combinations of neutrino mass states. And as these neutrinos propagate, a quantum mechanical process enables them to have a different probability of being detected as another flavor from the one that you started with. And so what our group is interested in doing is really understanding that flavor change process because it's very strange, it's very weird, and it's also very exciting because it's the first evidence of physics beyond the standard model because it proves that neutrinos have mass. Even though we've never measured the neutrino mass, we still know it has mass because of this flavor change process, and which was completely unexpected in the standard model. As I said, we're using beams of neutrinos created at Fermilab and directed towards detectors several hundred kilometers away to understand this neutrino flavor change process. And by having a beam of neutrinos, we're able to control both the energy of the neutrino and the distance that the neutrino travels, 2 parameters which are very fundamental to this flavor change process. Now, our experiment that is currently operating is called NOVA, and we are working on several different aspects of NOVA data analysis. The first one is obviously to measure these neutrino oscillation parameters, and the second is to look for evidence of even more beyond the standard model physics happening. The second experiment that we're working on is called DUNE, and it's in the process of being constructed. And in fact, you can see a picture from the inside of one of our DUNE prototype detectors behind me. Now, this is an experiment that's going to take the understanding and measurement of neutrino oscillations to the next level and enable us to look for evidence of CP violation of neutrinos. That is, whether neutrinos and antineutrinos behave differently with respect to neutrino oscillations. Now, if that's the case, it could be evidence for pointing to how our universe became matter dominated instead of being equal parts matter and antimatter. So both of these experiments are making very exciting measurements and have a lot of great work to be done on them. And on NOVA, you would have an opportunity to do cutting edge analysis of data. And on DUNE, you'd have the opportunity to build the next flagship experiment in the United States. If you have any questions, please contact me. I look forward to talking to you.